We'll start our discussion with a demotivational poster about teamwork. Ensuring that your hard work can always be ruined by someone else's incompetence. That one hits a little close to home sometimes, but it's funny. So we're going to talk about shaft design. This is chapter 12. And to design a shaft, there are several steps you have to take. The first thing is you have to know the rotational speed of the shaft. If you don't know that, you can't design the shaft, mainly because when you specify the rotational speed, it in part helps you determine the life. So there's tables in our book that tell us about how long typical types of equipment and machines should be designed to last. So a car should be designed to last, I think it's 3,000 to 4,000 hours, something like that. Industrial machinery, I believe, is about 20,000 hours. And sometimes you've probably not seen it. You've probably not been out in the real world much, but I remember seeing a machine at Grody that had come back in from wherever they had sent it, maybe China, I don't recall, but it was a machine they had designed. And I'm sure it has some shafts in it, but that's not really the point of the story. Anyway, the machine came back, and if a machine can look tired, this thing looked tired and worn out. There was grease all over it. It was parts hanging at a weird angle. Holes had been drilled and things added. And I think the thing had something like 20 million cycles on it, something like that. And it was just, like I said, sometimes people get older, they look tired, but this was a machine that looked tired. I've never seen such a thing. But anyway, so the rotational speed helps you figure out, if it's supposed to last so long and it's going to turn a certain speed, how many cycles is that? And so how long does this thing need to last? And that comes into play when you're talking about the fatigue strength. Now, really, most shafts are designed to last forever. If you think about the shaft in your car, a crankshaft, for example, in the engine, okay, it's one of many shafts in your car. If you think about that shaft, it's made of cast iron, so it actually doesn't apply to what we're talking about here. Sometimes they're forged, sometimes they're cast. But the thing about it is that there's some point where steel or iron-based metals eventually have an infinite fatigue life, whereas aluminum does not. You can't make an aluminum part that will actually last forever from a given loading and unloading cycle and magnitude of load. You can't do it. With steel, if you know the load and you never exceed it, you can make steel last forever. And actually, believe it or not, most components in your engine are designed, in fact, to last forever. And the reason for that is they see so many cycles. Think about your engine just going down the road, 2,000 RPM. Okay, fairly, relatively low speed. Highway speeds, 3,000 RPM is not unreasonable. But imagine you're going on vacation and think about that distance and how many times that crankshaft turns. In the life of the car, the crankshaft ends up turning over so many times that it may as well be an infinite number of times. Now, obviously it's not. But it's an extremely large number of times, so you have to design for essentially infinite life. And some shafts you'll design that way, other shafts you don't. So we have this metric, this rule of thumb that says, given a certain kind of equipment, here's about how many hours it should last. Of course, it may depend on the company you work for, right? They may make machines that last longer, or maybe you work for a company that makes stuff quick and, it's just a stopgap machine, something where, company X needs to finish their run of production and this machine will do it, and once it's done, they don't care what happens to the machine. So there's many different aspects here, but rotational speed is really starting to get at how long should this thing last. That's really what it's for. The torque that the shaft has to carry. The purpose of every shaft is to transmit power, and the way it does that is by rotating at speed with some torque. So torque multiplied by rotational speed is power. And now, of course, number of rotations times torque is a certain amount of work, but torque is another very important factor in designing a shaft. So you have to know these things before you can even begin to approach a reasonable shaft. Now, understand, we're not talking about shafts that are load-bearing shafts that don't rotate much. Think about, I don't know, I can't seem to think of something real good right now, but just think about a shaft on a swing set. You've seen some of the nicer swing sets. Essentially, the pins in them could be considered a shaft. And if that pin rotates in its bearing, that's really not the kind of shaft we're talking about. We're really talking about power transmission shafts. Shafts whose job it is to carry power from one point to another. So then the next step, after we know how much torque the shaft has to carry, we need to figure out where we're going to put everything. So you're going to have things like bearings, gears, belts, pulleys, sprockets, all these things, many different hubs potentially. Sometimes you have to support the shaft axially. So an axial bearing as well as radial bearings, all of these things have to be designed. They have to be chosen, hopefully with some good reason. So the location of bearings is also very important. You might consider how they're placed, and there are better and worse ways to place bearings. As a matter of fact, shafts that are so-called cantilevered require more material because the loads are more damaging to the shaft. And we'll talk about that more in just a second. So the location of bearings and exactly at what length along the shaft they're located is very important. The shape of the shaft in order to locate components is important. If you think about a shaft, typically there's multiple components that have to slide onto it. So commonly shafts are made where they're smaller on one end, they get bigger towards the middle, and then smaller toward the other end. Part of the reason for that is that a shaft is a lot like a beam, and so it has moment loads in it that are typically highest in the center. So that's part of the reason. The other reason, if you have something that has to go to the center of the shaft, well, you don't want to have the shaft the same diameter along the entire length. That makes it difficult to slide elements on. So you prefer to have, larger sizes in the middle, smaller sizes on the outside, so it's easy to just slip on a component, and then maybe the last couple of inches of the way have a closer size where it fits well. So figuring out exactly what the shape of the shaft should be. For another example, some places you want shoulders so that you can put a bearing or a gear or something up against a shoulder and hold it axially along the shaft. So locating the components is very important, and having a step in the shaft is a really way to do it. I'll use this shaft several times, so I'll go ahead and show it to you. This shaft has several features in it. I'll try to rotate it a little bit as I talk about it. It has a shoulder in it. It's got some threads on the end. It's got a couple of different keyways. You can see a Woodruff key here. You can see what's called a sled runner key here. You can see the end where it was held in the lathe as it was turned, and you probably can't see it on the video, but there's a fairly rough surface here. It's about like the grooves in a record, if you know what a vinyl record is. It's about like that. This section's a lot smoother. This section's smoother, and there's another shoulder in the shaft there. Now it's busted off on the end, so I'll show you that in a minute. But it's also got a groove right here, and if you put calipers on this section, what you'll find is that this section is smaller than this section. The reason for that is if there's an element that sits here, we want to be able to just slide it easily until we get here and then have a really nice fit. So the finish and the size here, the finish is smoother and the size is a little bit larger just because we're trying to make it easy. Now this groove probably served, I don't know what this came off of. It was in the school when I started. I've held on to it because it's so useful. But anyway, at this point, there's a place probably for a snap ring groove of some type so that whatever element goes here can't come off. You notice there's a pin that's been drilled here. There's an O-ring still in a groove here. So this is the kind of shaft we're talking about. You probably can't see it, but one of the tricks that's been used that I think is a bad idea, you want to try and avoid it, in the shoulders, they've actually, right next to the shoulder, they've actually used the lathe and gone in, and they've got what's called an undercut. So the reason it's undercut is because the diameter right here at the shoulder is actually less than the diameter on the bulk of the shaft. Now, of course, this is already a point with stress concentration. Giving it less material, in my opinion, is a bad idea. There are ways to avoid that. Maybe this designer couldn't, I don't know. But they similarly undercut near the shoulder here. Now, whatever this was used for, maybe it didn't really matter. Maybe the loads were so small and there were other reasons for making the shaft the size that it is. It didn't matter. They could just undercut and make their lives easy. But most of the time, if you avoid that, then you can have less material, in other words, less diameter of the shaft. There are more steps. Let's continue. So calculate the torque, radial forces, and bearing reactions. Now, before we said you need to know the torque, well, that's generally how much torque you're going to put into the shaft at one point. But torque can vary along the length of the shaft. If you think about several machine elements, like imagine one main shaft that drives several pulleys. Well, each pulley is going to extract some power, and therefore the torque going to the next element will be reduced. So we're talking about normal operation. Obviously something can happen where a belt breaks and no power is flowing out of that particular section, and so all the torque can go to the next pulley. These things are possible, but we're talking about normal operation when we design our shafts. Now the radial forces and all of the bearing reactions are really important because those are our lateral or shear loads essentially that cause moments in the shaft and can cause the shaft to fail. Those are the loads we have to design the shaft to carry. So guess what? We get to draw shear and moment diagrams. If you remember strength of materials, you've probably drawn these, and the thing is that actually it's a little bit harder this time because in the shaft you're going to have both a horizontal plane to consider shear and moment in, but also now a vertical plane, because all the loads, well, sometimes that doesn't happen. Sometimes the loads are all in one plane. In that case, you don't have to consider, say, the horizontal plane. But many times you have to consider both planes, so you end up with sort of a double beam, a beam in this direction and a beam in this direction. Now it's round, so the strength of the beam is the same in both orientations. But anyway, so we end up making shear and moment diagrams, and often in two planes rather than just a single. Now what we really care about is the magnitude of the loads along the length of the shaft. So after you've got your vertical and horizontal planes, and you've calculated the reactions in those two planes and all the forces in those planes, as well as knowing the torque down the length of the shaft, well, then you can draw your shear moment diagrams, locate points that have maximum moments, and take the square root of the sum of the squares. Basically what you're doing there is you're saying, okay, if I've got a moment in, say, this direction, and I've got a moment in this direction at some point in the shaft, I really have to take the vector sum. I don't really care at what angle it ends up being, but I've got to take the vector sum of those two moments to get the maximum magnitude of moment at that particular section of the shaft. So you'll see more about this in the example problems I work for you. Alright, step 8, select a material. Now this is the point where you've almost completely specified everything that you need to in order to calculate what the diameters have to be. And the way I help students understand this is, you know, you might be able to make a shaft out of a material as soft as butter, right, to do the job. The problem is it's going to be absolutely huge because butter has such low strength. But the stronger the material of the shaft, the lower diameters that will be required in general. Now I say that's all, that's not quite all. You also have to determine, are you going to have this machine used basically as it's cast? Will you do some machining on it? Is it machined out? You know, exactly how is it made? Because that in part determines how long that material will last and resist fatigue. In other words, its endurance strength. So there are some other things to consider. But once we've gone all the way through step 8 legitimately, then step 9, we can calculate minimum diameters. And the minimum diameters we calculate, there's actually two equations we have to use. I'll show you those in a moment. And then finally specifying the final dimensions. Now why wouldn't the numbers we calculate in step 9 be good enough? Well, we want to use preferred sizes. So if you calculate a diameter, a required diameter based on strength and the load and so forth, how likely is it you're going to get 2.000 inches? It's not going to happen, right? You're going to get some odd 1.893 or something, you know. We'll just round it up to a preferred size and you're good to go. So specifying the final dimensions is an important step and something that students often forget to do. So just because the equation tells you need a certain amount of material, that's great. That's not the size you're going to make it. You've got to bump it up a little bit. Now bearings are most often made in metric sizes, so technically you have to specify a metric size wherever the bearings will be located. Now of course on a print that's an English print you don't put a metric size and an English size there. That just shows that you really don't understand the difference between the two, or really it shows you don't understand tolerance. So what you do instead is you put an English size, you know, to the order of precision required, and then move on. So specifying the final dimensions again is to accommodate the real components and, you know, try to get to preferred sizes. Now sometimes a very particular oddball size is required, and I don't mean specified from the equations I'm going to show you, but for some other reason you need it, maybe to interface with an odd sized hub or something. In that case it's okay to specify whatever size you need and not a preferred size, but generally we want to go for preferred sizes. So what factors affect shaft design? Let's consider that now. Well, there's a lot of things to look out for. If you have a long cantilever, so imagine this shaft, it probably, well, I don't know if it was cantilevered or not. I'm guessing there may have been a bearing here. So this portion of the shaft would have been cantilevered out. And if this portion holds some type of machine element that has to transfer power, which it looks like it did because we've got two different keys here, whatever element was here twisting the shaft, well, that was a section that was cantilevered. And what we'll see later is anytime you have a gear, a belt, a pulley, anything like that, you end up applying bending forces to the shaft. And a belt is a classic example where, let's just imagine that we had a pulley out on the end of the shaft and we put a V-belt on it, okay, and we tension it up real good and run it. Well, what will happen is, and I'm going to use a lighter illustration for that shaft. That thing's heavy. So pretend this is my shaft for a moment. Okay, so here's our load, our lateral load out on the end, and our last bearing is, say, here. what that will tend to do is bend the shaft. Now, as the shaft rotates, the load stays in the same direction. So from the shaft's perspective, it's as if the load is rotating around, and essentially what's happening is we're doing this to it. Hopefully you can see the pin deflect, you see. And so that is a fatigue type load. That is something called fully reversed bending stress, because one particular element sees tension and then compression alternately, and of course it's varying in a sinusoidal shape. Now, if there's too much tension in the belt, what can happen is the belt will fatigue the shaft and break the shaft. So you have to watch out for that and make sure that the belt will not be over-tensioned and cause trouble. Another thing that can happen is something called whipping. If the shaft is rotated at its natural frequency, or at its critical speed, it's also called, what can happen is that anything that's offset, if you imagine this shaft, you build the shaft, you make it out of the best material you can, but is the center of mass going to be right dead on the center of rotation, or will all the elements be perfectly balanced where the center of gravity is exactly on the center of the shaft? No, of course not. So there's some distance from the rotation center of the center of mass. Now, as the shaft rotates around, that's like whipping a weight around, and what happens is that the shaft can hit its natural frequency, where every rotation causes the shaft to go farther and farther. It has to do with the stiffness of the material, and the geometrical stiffness, which is due to the geometry, the size of it. But basically you need to calculate the critical speed. Now, it's not really easy to calculate it. A better thing to do is to measure the critical speed, essentially the vibration frequency, which can be done by other techniques I won't describe here. One is a fairly simple technique. You listen to it ring, basically. You excite it and listen to it ring. But all that aside, if you can calculate the critical speed, you should. And really the calculation is not all that useful, as much as it is useful to know what you do to change the critical speed. One thing you can do, if you add mass to the rotating assembly, what will happen is the critical speed will drop. Now, that may sound like a bad idea, but think about it. If your target speed is, let's say, 1,000 RPM, and you've got a critical speed at 1,000 RPM, but you add more mass, that moves the critical speed, let's say, down to 800 RPM. Well, as long as you accelerate through that 800 RPM quickly, you're not at the critical speed anymore. You can get on the other side. You can leapfrog the critical speed. Of course, one solution, rather than adding more mass, is to increase the stiffness of the shaft. So one way to do that is to increase the diameters. Now, that also adds mass to the shaft, but typically the diameter will, despite the mass you add, it will increase the strength much more than the mass added, and so, or I should say, it increases the stiffness much more. And so that typically will move the natural frequency up, and as long as you never get up to the natural frequency, then you don't have any concern for the shaft failing due to that phenomenon. Now, shafts commonly less than 3 inches are just made out of cold rolled steel. You can get what's called shafting, which is high precision shafting. There's several different grades. You can get it more or less precise. Typically, if you get a shaft that there's very few features that need to be cut on it because it's close to the nominal size, typically what will happen is you'll just buy it about 1/1000th of an inch undersize. So if it's a 1 inch shaft, it's going to come in at 0.999, or maybe 2/1000ths undersized, 0.998. That's really common, and shafting is a special type. If you use cold rolled steel, cold rolled can't be just applied directly as shafting. It's not perfect enough. It's not round enough. It really does have to be turned. But shafting that is already made, if you cut a key in it or you cut features in it, a lot of times you have to straighten it back out, because when the shaft is made and it's precise, what will happen is it has stress, remaining residual stress in the surface material, and when you cut features in it, it deflects enough that it has to be straightened. And that's a whole art to itself. There are, you can imagine that many shafts aren't worth straightening, but shafts from things like large ships are commonly straightened in order to improve their performance and get the center of mass closer to the center of rotation, often is the goal. And of course reduce stress on bearings and things like that. Between 3 and 5 inches you can use cold rolled, you can use something that is just turned, but greater than 5 inches are typically only turned. In other words, put on a lathe and machined in order to create the shaft. So all large shafts for things like large ships, any cruise ship shaft, etc., is going to be turned. It won't. I mean, I suppose it could be forged, but you need features on it that are precise, so at least sections of it are going to be turned. What materials do we make shafts out of? Well, we're going to approach this from the ductile material approach, and basically use what's called the maximum normal stress theory of failure. If you need a very complicated shaft, like a crankshaft that's going to be made out of cast material, then again you need something different than what we're showing here. This is just for shafts that look generally like this thing, okay? Things that are common machine shafts that are custom. Now, most shafts are made of steel that we will consider, and so they'll have similar elastic moduli. In other words, their material stiffness property will be pretty much the same regardless of what alloy you choose. You can choose some super strong alloy, and yet its stiffness won't be any different. It just is stronger. Or even a weak, a 1020 steel, for example, will still have about the same material stiffness. It just can't take as much load as something that's stronger. So the stiffness of the shaft will be a function of geometry primarily, and not the alloy. Now, it is true that each steel and alloy has slightly different elastic moduli, but it's not enough difference to warrant changing material just to get stiffness. You really have to change the diameter to get stiffness out of the shaft. So here's a typical shaft. You can see a gear mounted all the way on the left. There's a bearing at B. There's another gear at C, and finally another bearing at D. Now you notice that gear A is cantilevered out off of the bearing B, and so that is a section of the shaft that's going to experience potentially much higher bending loads, whereas the gear at C is straddle mounted, and so the effective moment in it will be in the middle of the shaft there, will be lower. Now, here's what I mean by you have to design it. You have to decide how far apart each of these elements will be, where they'll be located. Are you going to cantilever, or are you going to straddle mount everything? What kind of features are necessary in the shaft? Do you need shoulders? You see at least, what, 1, 2, 3, 4 shoulders, one shoulder for each element, so that that element can be located precisely. Now, you notice there are no retaining ring grooves for the bearing, but there are for both gear A and gear C. Why is that? Well, commonly the bearings are held in place by a housing, so the housing has features that prevents them from moving. Now, one problem, if you put a shoulder on the opposite side in the housing on one bearing and also on the other bearing, as the shaft heats up and the case has a sort of delay in heating up, the shaft can end up generating very high stresses and pushing the casing apart. So it's pretty common in design to have a housing that locates the shaft axially at one point and the other point floats, or has something that prevents the shaft from moving too far, or the bearing from moving too far axially, but there's typically a lot of clearance there available. You have to decide what kind of radii you're going to have on the shoulders, right? The tighter the radii at the shoulders, the more stress concentration there's going to be, the higher the stress concentration factor. So you'll notice that R2 in the figure near bearing at B could be a lot higher. It could be a lot more generous than the radius at the shoulder itself, R3. And the reason for that, of course, is that the bearing has an inner diameter and has to slide up against the shoulder. Now, often in bearings and gears and things, you add a chamfer or some type of feature that breaks the corner so that it can slide up against a corner with a reasonable radius in the shoulder. You don't want the radius R3 to be very tight if possible. You'd like for it to be a fairly large radius to avoid stress concentration in the shaft. But the inner diameter of the bore of the bearing has to accommodate that, and there's only so much space there. It's the same argument about R4 and the gear. So chamfers are added to gears and bores of bearings and things for two purposes. One reason is so that you can get the darn thing on in the first place, get it located, helps you locate it easier, but also to accommodate radii at the root of the shoulder. Now you'll notice we have a profile key seat at A and one at C, as well as they've got one shown at B, but that's not correct. You typically do not key the inner race on a bearing to the shaft. Now I suppose it may have been done at one point. I've never seen it, but that's a mistake in the drawing, in my opinion. It should not be there. But I guess I should get into an editor and edit this. I never really noticed it till now. At C, the gear, that keyway there, is correct, so it should be colored white so you can see it as well. But the one at B is completely in error. But really what we're trying to do, given all these locations and figuring out what all the loads are everywhere, what diameters along the length of the shaft are required. And you know, a lot of students feel like, well, I want to calculate wherever the maximum load is, give me that diameter, I'll make the entire shaft that diameter. Well, that's not necessarily the best, because it's convenient to have the shoulders to locate the bearings. It's convenient to have the shoulders to locate the gears. It's nice to be able to reduce the mass of the shaft so that you don't have to have as much weight by tapering it along the ends. It's nice to taper it towards the ends because then machine elements can be put on and assembled easier. So there's many reasons to turn the shaft and have different diameters along the length of the shaft. Don't be a lazy designer and just try to get one diameter and be done with it. Now, the power in the shaft, the power that the shaft transmits, and the torque are closely related to one another. You'll see the power-torque speed equation appear over and over. Now, technically from physics, power is simply torque times speed. But it is convenient to have power in particular units of horsepower, torque in inch-pounds, and speed in revolutions per minute. If that's the case, you really don't want to go and figure out the conversion factor every time you do this. So you'll see me write this equation and use it over and over. Power equals torque times speed divided by 63,025. Some people just use 63,000. A more accurate conversion factor is 63,025. What this does is it allows us to put power in horsepower, torque in inch-pounds, and speed in RPM, and the units are then consistent by that conversion factor of 63,000 roughly. Now, sometimes you want to use torque in foot-pounds, for example. Page 695 has a whole nice table of conversion factors in both metric and English units. So I highly recommend you go to that page right now, bookmark it, because you'll see the conversion factor of 63,025, but you'll see the conversion factor, it's 5,000 some odd when you want to have torque in foot-pounds instead. This is an equation worth memorizing. If you don't want to memorize it, that's fine. By the end of the class, you probably will have it memorized, though. So what are the effects of the machine elements on the shaft? Well, gears end up, it turns out, because of the involute profile, which we'll learn about later, gears tend to push each other out of mesh. There's a radial force that's generated because of the shape of the tooth that push them apart. Also, the whole purpose of the gear is to transmit torque. So there's essentially force trying to turn the gear teeth, okay? And that force is a tangential load. It's the whole point for having the gear in the first place. Now, obviously, the tangential load, W sub t, is related to the torque, but it turns out that because of the shape of the teeth, the radial load is also related to the tangential load. So there are equal and opposite loads on the gears. So for example, if there's a radial load and tangential load on gear B, which is the larger gear, then there are equal and opposite loads on gear A, and depending on which shaft we're designing, the shaft that A rides on or the shaft that B rides on, depending on which we're designing, we need the loads, you know, in the correct direction. So you really have to think about the proper direction for all of these loads. Now here's some relationships that are very important. I don't remember the page right off for this, but you will want to bookmark it. It's in chapter 12, but it says that the torque is related to the tangential load. You can see the tangential component in something called the pressure angle. Don't worry about the pressure angle right now. I will always give you the pressure angle for shaft problems if you need it. But the pressure angle is called, or it's given the symbol phi, and the tangential load and radial load are related to one another by that pressure angle phi. In fact, the radial load is the tangential load times the tangent of that angle. Commonly it's going to be 20 degrees because gears come in only standard, well, I mean, I guess you could make anything you want, but standard pressure angles are 20 degrees. 14.5 degrees is an obsolete standard. There's 20 and 25, I believe, that are standard for spur gear teeth, and other angles for some other gearing. But anyway, the point is that if you need torque in terms of the tangential load, that's the first equation. If you want the tangential load in terms of the torque, that's the second equation. They're the same thing, just rearranged. And of course, D is the pitch diameter, not the diameter of the shaft, but the diameter of the machine element, the gear in this case. And let's see, so notice that the radial load is written in terms of the tangential load. The reason for that is because the tangential load is really the whole point in having the gear. That's what causes the gear to tend to turn and transmit torque. And then the normal load, this is just included for completeness. We typically won't even care about it. The normal, at least not right now, not till we get to gears. The normal load, you'll notice, is the vector sum of the radial and tangent load. It's the actual load on the gear tooth. But the tangential load is so important, we typically write the normal load in terms of the tangential load. Again, because the tangential load is our goal. It's what we're trying to accomplish. And it's something you typically calculate from torque, obviously. You know how much torque, and because you know how much power has to be transmitted, and so you end up backing out the tangential load first. Helical gears are a little more complicated because the teeth are at an angle to the shaft of the gear. So not only do you get a tangential component that you want, a radial component that comes from the shape of the gear tooth, the involute shape of the gear tooth, but you also get an axial load, something that tends to try and push the gear along the axis of the shaft. And there's several equations here relating all of those together. W sub x is the only new one, and it involves the axial load on the gear. You can just think of Wx as something that tries to push the gear along the length of the shaft, the axis of the shaft. Now there is another variable involved here. It's a it's a psi. This is the symbol they use for psychology. It's sort of the trident or the pitchfork. And this is the so-called helix angle. It's basically the angle of the gear teeth on the helical gear. We'll talk more about all of these loads when we get to helical gears and we're designing them near the end of the course, but for now just know that these three are related to each other and you've got equations here to relate them. So I would have to give you the pressure angle phi as well as the helix angle psi. Now in helical gearing there is a difference between the tangential pressure angle and the normal pressure angle, but don't worry, I'll make it clear which one I'm giving you, and I'll make sure it's easy for you to deal with it if I ever give you helical gear teeth. So I've already talked through all of this. Again, the W sub n is the true normal force. It's the force that's actually applied to the gear teeth. Gear teeth are always lubricated. You should always put oil between them, at least for decent design. I'm sure there's some machines that don't have it, but and some gear materials are self-lubricating, some plastics, etc. But the point is that they can slip. They do slide on one another. And so the oil basically makes the force along the tangent of the surface zero no matter what direction you're looking at. So the only load that can really exist is the true normal force, but that normal force breaks down into the components, the tangential, radial, and axial components as you saw on the previous slide. So here are the equations you really need for helical gear teeth extracted from that slide. If you understood everything I said, great. If not, here's what you really need. There are some more complications that come from bevel gears and worm gears. We'll look at those in Chapter 10. For now, I just won't give you this type of gearing when you're trying to design a shaft, so don't worry about it right now. What about chains? Well, we haven't really learned much about chains yet, but for chains, there's always a tight side and a slack side. Think of your bicycle, right? When you pedal your bicycle, it's the upper chain that is in tension pulling the rear sprocket on your rear wheel. Okay, the lower side is slack. That's the whole reason that on a multi-speed bike you have to have what's called a derailleur. It's basically a springed set of sprockets that take up the extra slack in the chain. And the reason they're slack is because, of course, you have to accommodate all of the different gear ratios, and basically you need a longer or shorter chain depending on what the gear ratio is or the sprocket ratio is. So typically we neglect any force on the slack side. You typically don't want to install a chain where there's preload. You want some kind of tensioner, but not anything that gives you any significant force in the slack side most of the time. So we'll typically neglect that, and the force in the chain can be calculated. You see the equation there based on the diameter of the sprocket and the torque. It's a simple equation. It's just basically a moment equation, force times radius equals torque. But we'll neglect any force in the slack side of the chain, whichever that happens to be. And we're going to neglect something else. Since usually the angle of the force, Fc, the force in the chain, is close to the direction between the center lines of the sprockets, we'll typically neglect that little angle phi. And we'll just say that the force acting on the chain is just acting directly between the centers of the sprockets. Now, belts, on the other hand, cause force on shafts as well. As a matter of fact, in a belt, say, think of a V belt, you have to tension it where there is pre-tension in the belt. So both sides, the tight side and slack side, have significant force in them, and we'll call that F1 and F2. Of course, you know, the force in the tight side is larger because that's technically the driving side. But what we're going to do is basically assume that the bending force on the shaft is just the sum of those two forces, F1 and F2. Now, the magnitude of F1 and F2 and the relationship between the two depends on how tight the preload is made. Whenever you put a belt on, you have to give it some initial tension before operation. Now, during operation, obviously, there has to be one side that becomes even tighter and the other side has to become even looser. Thus the name the tight side and the slack side. And if you don't give enough pre-tension, the slack side can actually whip around a lot, and that's very problematic. But depending on what the pre-tension is, that will change the relationship between F1 and F2, and it'll increase the total bending force. I mean, the tighter the initial tension in the belt is, the more bending force there's going to be on the shaft. So how do you accommodate that so you can do calculations if there's a pulley on the shaft? We have to assume that the belt is properly tensioning, and reasonable proper tensioning is where the tight side has about 5 times the force as the slack side. That's sort of a rule of thumb. It's a good tensioning in the belt for good service life of the belt and good operation and so forth. Now, it's not obvious, but if you take that relationship between F1 and F2, you can actually come up with the total force in the belt. And so here's the equation that you need, and it is from, it's equation 1212, it's on page 457. So I would suggest that you go and look at this, look at the details of how it's derived. You'll see me use it in example problems possibly, but it's pretty simple. But this is a page that deserves a highlight, and the equation 1212 certainly does, I'm sorry, it's a page that deserves a tab, and is certainly an equation that deserves a highlight. Now, couplings are things that couple shafts together, typically axially. Now, these typically do not have any side loading, so they transmit torque only and don't add any bending or any axial loads to a shaft. Now, since keys are features that have relatively small sizes and they introduce stress concentration, we need stress concentration factors. There's a lot more to stress concentration factors than what you're going to see here, because the inside line on the key can be cut with many different potential radii. You don't have a zero radius in those corners. So depending on the requirement of how close the key has to fit, and how the corners of the key are broken or not, the stress concentration that the key actually provides will depend on that inside radius to a large extent. We're going to simplify all that because that is not our focus in this class. We're going to assume that all profile key seats, which you see at the top, have a stress concentration factor of 2, and all sled runner key seats have a stress concentration factor of 1.6. These are reasonable starting points, but anytime you're designing a shaft, you should really look up a table that gives you the stress concentration factor as a function of that inside corner radius, because it does make a difference. It's the same story for shoulders in shafts. Shoulders in shafts can either be, for our purposes, sharp or well-rounded. Again, there's a lot more to this, and if you've gone through Strength of Materials with me, you know that we had a whole appendix in the back of the book that was devoted to calculating these stress concentration factors based on the radius, the smaller and larger diameter, and so forth. Again, that's not our focus in this class. So we're going to take, for sharp corners, we're going to take stress concentration factor to be 2.5, and for well-rounded corners, we're going to take the stress concentration factor to be 1.5. So while there's a lot more to this, we're just going to take a sharp shoulder to be something that we're going to shove a machine element up against, and a well-rounded shoulder to be something where we just want to transition in size. So the picture here shows a mating element of coming up against the shoulder with a well-rounded shoulder, but most of the time we're just going to assume that well-rounded shoulders are not those shoulders where we're going to mate a machine element against. Now, if you have a groove, you notice that shaft I showed you has both a sled runner and actually a woodruff. This is not a profile key seat. A profile key seat, you just plunge an end mill and go down the length and then make it size. This is a different type. We're not going to consider this type in our shaft design. The stress concentration factors are a field of their own, and you can look them up in references. But you'll notice that we've got a snap ring groove here, we've got an oil ring groove here. Any groove like that in the shaft typically will have a fairly sharp corner on the inside. And so in those grooves, we're going to take the stress concentration factor to be about 3 or so. And these are fairly common. Anytime you have a shaft that is splined, or even regular shafts, these are elements that either typically are used for sealing with an O-ring, or they're used for snap rings to axially prevent motion of machine elements on the shaft. Alright, so we finally come to our first equation for sizing sections of the shaft. Now this equation is the less important equation. It is the shear force equation. It only considers shear loading. So think of all of the radial loads in the shaft and not the moment at all. Okay? This equation involves calculating a required diameter based on the shear load in a section of the shaft. Now where this equation is really important is more out towards the edges of the shaft where there's no significant moment. That's where this equation dominates. Well, I'll show you another equation in just a minute that dominates the more central sections of the shaft. So this doesn't include anything about torque, doesn't include anything about bending loads, and really the two equations I have are not equations that accommodate all three things. I'm not going to give you an equation that accommodates shear loading, moment loading, and torque loading. The problem with that kind of equation is it becomes very complicated very quickly. Most of the time you can separate out shaft design into designs that involve essentially a shear load at the ends and moment and torque in the middle and neglect the rest of it. And it's good enough, especially once you add a little bit of material to go to preferred sizes. You're usually well within an acceptable range of operation. So here we're looking at those places where there are only significant shear loads. So you'll notice in the equation we've got a V for shear, and that V is what you would get from your shear diagram. N is a design factor of safety, so again that's something that bumps up the size of the shaft required based on whatever you want. KT is a stress concentration factor, 2.94. That has to do with the geometry. Don't worry about it, it's just something you need to use. And then SN prime, what is that? Well, SN prime is the so-called modified endurance strength. Now that's all the way back in chapter 5 or 6. It's about the only thing we reference in the class that's in chapters 1 through 6. Now have your book handy when you go through the example problems, because I will certainly point out pages in those chapters, either 5 or 6, I can't remember right now, that you will need to reference for shaft design, and in particular to get this modified endurance strength. So what we're really doing is comparing the shear load to the modified endurance strength. That's what you do when you take a ratio, right? I mean, think about a ratio. Say you want to buy a Corvette. Fun. You just got your first job. You landed a great job. Let's say they gave you, let's have some fun here. They gave you a $60,000 signing bonus. Whoopee, right? Well, you could buy 2 Corvettes at that price, right? How did I figure out 2? Well, I'm comparing your bonus to the cost of a Corvette. If a Corvette costs roughly $30,000, then $60,000 over $30,000 is 2, right? That's that comparison ratio. We use it all the time. So you're really comparing the shear load, V, to the modified endurance strength, SN prime. And the reason you compare the shear load, which is a radial load, to the endurance strength is because, think about it, the shaft's going to rotate, isn't it? And so from the shaft's perspective, the shear load is rotating around, and so now we're talking fatigue, right? So we want to compare the load, V, to the fatigue strength, SN prime. And so that's why we perform that comparison or take that ratio. Now the bigger equation, the more important equation I would argue, is the one that involves moment and torque together. So you see we're taking sort of a vector sum of 2 loads, M for moment and T for torque. There's more to it than that, but stay with me. Essentially we're taking the square root of the sum of the square. So we're adding together the effect of the moment and the effect of the torque, which both are vectors, and so legitimately cause a stress that would be a vectorial addition. Now notice that the torque is not as damaging, so we take 3/4, and again this comes from geometry, don't worry about it, it's strength of material stuff. But you'll notice that the torque is being compared to the yield strength, SY. Whereas the moment, M, okay, it's got a stress concentration factor there, but it's being compared to the modified endurance strength. Now why the difference? Is this a misprint? No, it's not. The reason is because the torque in the shaft, most of the machines you're designing with this kind of shafting will have essentially constant torque. You're constantly transmitting power, and yeah, there's some variation in it, but it's not all that large. It's not like a moment or a shear that, you know, the vector is rotating around the shaft. So the torque is essentially a constant. We're going to neglect any fatigue type torque loading, and so we should only compare it to the yield strength of the material, because we don't want the torque to cause yielding in the shaft. But the moment, again, is a fully reversed bending moment, regardless of how you design the shaft. So, well, I guess if you have a dead shaft that it's not, but that's not the usual case. We're talking about mainly rotating shafts in this chapter. So we have to compare it to the modified endurance strength. Now, N is a factor of safety, 32 over pi and the 1/3. This is all geometry and, you know, rearranging the required size from the strength of the material. And so here's where you know, we're neglecting shear, because, as I said, this is the equation that usually will apply more towards the center of the shaft, and the other equation, the shear equation, applies more towards the ends. But when you size the shaft, one thing that's really important, you need to calculate a minimum diameter from both equations along the entire length of the shaft. So it's very handy to put this into Excel, because you really don't want to apply this equation, you know, 10, 20 times along the length of the shaft. You want to apply this equation, and you want to have your moments and torques and shears all set up from your shear diagram in Excel, so that you can just drag down and calculate required diameters along the entire length of the shaft. And you'll see me do that in the example problems. I also made a SolidWorks model to hopefully help you understand this concept of a horizontal and vertical shear and moment plane, and how you have to add those loads vectorially. So we end up using these equations over and over again. You can't just say, okay, I'm going to design a shaft, I'll use this equation once. It doesn't work that way. You apply this equation multiple times along the entire length of the shaft.